Since the engine's performance is much more critical of air-fuel ratio than ignition timing, we always want to start with the fuel table. The numbers we entered into the ignition map during the table configuration should be adequate for now to have the engine running safely without detonation, but while completing the fuel tuning, you should still use knock detection equipment to listen for detonation. The aim with steady-state fuel tuning is to adjust the numbers in the main fuel table to achieve our desired air-fuel ratio. It sounds simple, and it is, but there are a few tricks that we're going to discuss that will make the job easier and give you a more accurate result faster. With our Motec M150 example, it's important to make sure that we adjust the VE table until we achieve the target lambda number that we've chosen and entered into the aim lambda table. If we do this properly and the injector data is accurate, the numbers entered will be a true representation of the engine's volumetric efficiency. The advantage of a proper VE-based tuning method is that once we have calibrated this table properly, we don't need to touch it unless we change the airflow through the engine. If we want to change the air-fuel ratio at a particular point, we can just adjust the aim lambda table. This is a technique more ECUs are adopting, so it's good to understand the principle. On a conventional ECU that uses a millisecond-based fuel table, we are still adjusting the fuel table numbers to achieve our desired air-fuel ratio, only this time we may not have an aim lambda table to work with, and we may need to decide manually what air-fuel ratio we want to run at a particular point in the map. To make the tuning changes, we want to drive the car on the dyno and visit each site in the fuel table. Since we're starting from a blank fuel table, we want to start with as little RPM as possible and as little throttle opening. In this case, I'm going to start at 1500 RPM. Once the engine's settled and stable at 1500 RPM, we want to reduce the throttle to access the lowest cell in the 1500 RPM column we can reach. If we back off the throttle too far, the engine will just slow down since the dyno needs some amount of torque to turn. Now we should be running in steady state and ready to make some tuning changes. Before we do though, we want to make sure the engine is running in the centre of the cell we're about to tune. The M1 ECU has a nice target feature which shows you how close you are to the centre of the cell the cursor is currently in. You can adjust the dyno speed as well as your throttle position until you are centred in the cell, and now you can make changes. What we want to do is check the measured air-fuel ratio and compare that with what we want. If there's a difference, then we can correct this using the have over want formula we learnt in the EFI fundamentals course. Just take the measured air-fuel ratio, or the air-fuel ratio we have, divide it by the target air-fuel ratio, or the air-fuel ratio we want, and you'll end up with a correction factor. If you apply this to the number in the current cell, you'll end up with the right lambda value. Once we've tuned the first cell, we want to increase the load by applying more throttle until we're in the next load zone. Before we do this though, we can save time by copying the number from the cell we just tuned and moving it up into the next cell. Since airflow will generally increase as we open the throttle, we can assume that the number we will need in the next cell is going to be close to that of the cell we just tuned, and perhaps a little larger. Copying the number ahead like this means we're already going to be close when we get into the next cell. This reduces our tuning time and also means there's less chance of the engine running lean while we get the tune correct. From here, the job is just a case of repeating the process of tuning the cell, increasing the load, and repeating the tune until we reach full throttle. At this point, that particular column of the fuel map is tuned completely, and we can increase the RPM to the next RPM range and repeat it again. Before we do this though, we want to copy the numbers from the 1500 RPM column we just tuned and paste them into the 2000 RPM column. This means the numbers are going to be close at this RPM range when we start tuning. Since we can expect the engine's VE to increase as we move from 1500 to 2000 RPM, the numbers are likely to be higher than what we had in the 1500 RPM column, and there are a couple of time-saving tricks here to help you. First of all, before tuning the 2000 RPM column, I'll usually add 5% to the entire column. This is a guess at how much I expect the airflow to increase at this RPM range. We can now start running the engine at 2000 RPM, and again we want to use as little throttle as possible to achieve the minimum load we can. At this point we can check the AFR and see how it compares to our target. All going well, it should already be very close. If there is any difference, we can use our have over want formula again to calculate a correction factor. This time though, we'll start by applying it to the entire column. This should get the entire column closer to our target before we start tuning the individual sites. Now we can repeat the earlier process and tune each individual cell, increasing the load until we reach full throttle. This is the process that we use and repeat as we increase the RPM, and you'll start to see a pattern emerge of what the fuel table needs to look like. The have over want equation is great, but if your lambda number is very close to your target, you may find it quicker to make small manual changes to the fuel numbers. If you're tuning in lambda numbers, you can also manually judge what percentage to change the fuel table. For example, if we're running at lambda 0.95 and we want to be at lambda 1.0, I'd start by subtracting the difference of 0.05 or 5%. This will get us close and we can manually adjust for any remaining error. At higher RPM, this process can put a lot of stress on the engine, and we may also find it harder to control the engine temperature. The reality is nobody ever really drives their car at part throttle and 6500 RPM for extended periods of time. What I mean by this is there are certain parts of the fuel map that we don't need to be quite so accurate about. My rule of thumb is to use steady state tuning up to about 2/3 of the rev limit RPM. In our example, I'm going to tune to 5000 RPM in steady state. From here, we can simply copy the table across to the right to fill out the remaining cells. What we can then do is check each of the higher RPM rows briefly and adjust the entire RPM column up or down until our mixtures are about right. I do this by highlighting the entire column before I start tuning. I then bring the engine up to the required speed at low throttle and smoothly increase the throttle opening while watching the air-fuel ratio. I'll then increase or decrease the entire column until the mixture's safe. Again, since the engine will only operate here during transient periods, we don't need to be super accurate, and I prefer to have the mixture a little richer for safety. We can then repeat the process for the rest of the columns in the map. The side benefit here is that we'll have the full power tune closer when it comes time to do the full power ramp runs. So by the end of this module, you should know how to use the dyno to control the engine in steady state and how to adjust the fuel map to achieve your target air-fuel ratio.